All right, guys, let's go over the capacitive prox sensors. So they look very similar to the inductive sensor. If you take a look at these cylindrical housings right here, this M12 or this M18, they look almost identical to the ones that we saw. This one has a plastic housing. The inductive sensors we saw had a metal housing, but they're very similar in just looking at them. They do come in other forms though. So depending on your applications and mounting considerations, they do come in this form as well. On the front, it's going to tell you what each of your different color codes correspond to, or it's going to provide you with a wiring diagram. You could just make this guy out here, or right here, there's a wiring diagram for the SiC manufacturers. All right, let's go through the basics of these guys. So capacitive sensors are, again, non-contact switches. So they don't have a contact that's going to bounce. It's most likely going to be a transistor that's firing on and firing off and providing an output. So you don't have to worry about a contact bouncing and giving you multiple counts for each object going in front of it. Capacitive sensors can detect metal objects, non-metallic objects, solids, and liquids. But if you were trying to detect a metal object, I mean, you're most likely going to use an inductive prox sensor. It really depends on your applications. So they can basically look at anything. You know, metallic, non-metallic, solids, liquids. Let's get into more specifics as we go. Okay, they're similar in size, shape, and concept to the inductive prox sensors. There's like a resonant circuit that happens inside that we'll take a look at in 2 seconds. And basically what you're doing is you're either creating another plate on the capacitor when you put something in front of it, or you're changing the dielectric in the front of it. It says, however, unlike inductive sensors, which are used to induce magnetic fields to sense the objects, capacitive prox sensors react to alterations in the electrostatic field. So again, when you're putting a metallic object in front of there, you're basically creating another plate on the capacitor. If you're putting a non-metallic object, then you're changing the dielectric that's between the two plates of the sensor. Okay, capacitive prox sensors measure changes in capacitance, which is caused by the approach of an object to the electrical field of the capacitor. Two small plates that form a capacitor are located directly behind the front face of the sensor. So the inductive sensors had a coil. These guys have the two plates of the capacitor. Now, capacitors usually, if you take a look at the basics on these guys, a crude capacitor would have one conductor, another conductor, and then an insulator between it. And the name that they provide for the insulator is called the dielectric. So the way that you can change the capacitance or the amount of charge that can be held on a capacitor would be by changing the distance between the plates, by changing the surface area, or by changing the type of dielectric. So these sensors are going to sense something in front of it by a change in dielectric. So it's hard to jam something in between these two plates. So why don't we open those bad boys up, right? So you can see here that we have now taken the capacitor and now opened it up so that the front like the inside of each of the plates is now pointing out to the front face of the sensor. Now, whatever we put in front of this sensor is going to change the dielectric that's insulating those two plates. Okay, so for these guys, remember we said that they'll look at conductive materials and non-conductive materials, right? So basically by putting a non-conductive there, it's saying that it's improving or changing the dielectric constant from air to whatever you've placed in front of it. And by placing a conductive piece, like a piece of metal, then you're basically adding a plate to form two capacitors within there. Either way, you're going to be changing the capacitance value of the capacitor. Let me just give a shout out to Terry Bartelt. Give me 2 seconds, I'll go to the website to show you where his textbooks are. Okay, so this is a great book. It's got all kinds of stuff on AC motors, DC motors, sensors, drives, electronics. The gentleman's name is Terry Bartelt. He's got a number of different animations, flash animations on the web that will help you out with different topics. And if you just type in Terry Bartelt to your local Amazon, you'll be able to reference all of his textbooks. I highly recommend this textbook, Industrial Control Electronics. All right, let's get back to capacitors. Okay, so we're either going to be changing the dielectric or we're going to be adding a plate to the capacitor. Either one of those guys is going to change the capacitance value inside of the circuit of the sensor. If we take a look at Terry's picture of the inside components of this sensor, it's very similar to the inductive sensor that we looked at before. Right? On the output side, it looks like we have a transistor here. And if we look at the oscillator stage, instead of having a coil on the front face, there's our 2 plates of the capacitor, right? So we put the 2 plates of the capacitor. Anything that we put in front of this is going to change that capacitance value. So this op amp right here is looking at the output of the capacitance of the front face of the sensor, and it's got a reference voltage that's referencing that voltage divider. If there's any difference between these voltages, then we know that we're going to have an output from this op amp circuit. That output is going to go out. We're going to go through the demodulator stage. There's basically like a filtering stage with a diode and a capacitor for filtering. The output from here might be an analog output. So if we wanted to have an analog sensor, then we wouldn't have this Schmitt Trigger stage. But the ones that we're using are a digital output. They basically turn on or turn off. So this analog signal goes into the Schmitt Trigger. I love saying Schmitt Trigger, right? This takes the analog, changes it back into a digital output, and then that is applied to our transistor output. So these sensors don't have a contact. They've got transistors, and you can fire a transistor on and off thousands of times a second. So these capacitive sensors are amazing in that they can sense anything that's in front of them, and they can give nice clean counts thousands of times a second. Okay. In addition to that, we've got some protections here. Let me check the next slide and see if I've got it on the next slide with our different protections. Right on. So there's our oscillator stage, right? We can take a close look here. There's our capacitor on the front going to the op amp. There's our reference voltage to our voltage divider. The output of this op amp, if there's any difference between these guys, then that will send out a signal to the filtering or the demodulator stage. That goes into the Schmitt Trigger. We know from previous classes that the Schmitt Trigger basically takes an analog output and brings it back to a digital output, and that's going to provide us with that 24 volts on and off once we fire on or fire off this transistor right here. Excellent. So taking a look at the conductors on here, this looks like it's a diagram of a 3-wire capacitive sensor, in that we've got 1, 2, 3, or 1, 2, 3 conductors that are coming out of this sensor. The positive is always the brown conductor. The negative is always the blue conductor. And this output conductor right here is going to be our black conductor. So standard 3 wires are that the positive is the brown, the negative is the blue, and whatever the output is the black. All right, let's take a look at this guy and see whether it's a PNP or an NPN output. Well, it looks like the load, right? So that's our load or our PLC. Or when it comes to the labs, that's going to be our light bulb. And so normally this is going into a PLC. It looks like the PLC already has a reference to the positive. And the switch, so if we follow this circuit through from the PLC down here to the switch, the transistor is acting as the switch, and the switch is in the negative portion of the circuit. So this one is an NPN output or a sinking output, in that this here with the PLC already has a reference to the positive, and we are switching the negative. Okay? So with this guy, we've got also a number of different things to protect the inside components, or primarily to protect this transistor from smoking. So we've got an over voltage protection with the zener. So if there's a spike of voltage that comes through, the zener is going to conduct and bypass our transistor. We've got a diode here. So the diode is going to provide us with the reverse polarity protection, in that we have to connect the negative or the blue to the negative, and we have to connect the brown to the positive. If we don't get that polarity correct, then this diode is going to block that current. So over voltage reverse polarity protection, and then finally, if we have too much current flowing through, so say we're trying to turn on a load that's too large for the output of this transistor, then we've got an RTD that's in series with the transistor. An RTD is usually used as a temperature detector. It's a resistive temperature detector, but we know that as with an RTD, as the heat increases, the resistance increases. So if we get too much current that's flowing, then this bad boy is going to heat up. As it heats up, its resistance is going to go up, and that's going to create like a short circuit protection in that as it heats up, then the resistance will go up, and that will drop the current, hopefully before the transistor smokes. Okay, so let's see how this guy works again. We're going to put something in front of the sensor, right? Once we put something in front of the sensor, the op-amp circuit sees the difference between that capacitance and our reference voltage, goes through a filtering stage, may go into the Schmitt Trigger stage, and then goes to our transistor. Once the transistor fires on, then we'll be able to have conductivity between our positive, in this case through the PLC, through the transistor, and then back to the negative. Excellent. So basically what it's doing is it's changing the oscillator frequency of that capacitance portion on the front face of the sensor, and that changes the sensor's output. Right? So you can see here that the oscillator is stopped with no target present. Once that capacitor comes into place, then the oscillator goes at a higher frequency, and then we're going to get an output. I like looking at it better, just that like the op-amp is basically looking at two different voltages. The voltage coming from the capacitor and the voltage at the reference voltage that we saw between the two resistors. Capacitor sensors detect all materials that are good conductors and insulators that have a relatively high dielectric constant. Capacitive sensors can detect plastic, glass, water, wood, right? Anything there that has a higher dielectric than air. Nominal sensing distance. Okay, so there's one of the limitations on this guy. Nominal sensing distance are only 3 mils to like 15 mils. So this thing isn't going to see 6 feet in front of the sensor. You got to be basically, half an inch to an inch in front of the sensor in order to change the capacitance value. Maximum sensing distance depends on the physical and dielectric characteristics of the object. If you want to have more sensing distance, you need to have a larger capacitor. So larger the dielectric constant, the easier it is for the capacitor sensor to detect. And generally an object with a dielectric constant greater than 1.2 can be detected. So the reference is air. So anything with a dielectric that has, around 1.2, it should be able to see it. Where do they get those dielectric constants? Well, we can get them from a chart here, right? So our reference is air. So it looks like, something like, let's see, something that has a low value, right? Like lime has a dielectric constant of 1.2, right? Teflon will most likely be seen, but it has a low dielectric value. Something that would be easily seen would be anything that has a water content. So I'll get you guys to put your finger in front of the sensor. Your blood is full of water content. So look at the dielectric constant for water. It's at 80, right? So anything with water, and you look at the difference between dry wood and moist wood. Dry wood's hard to see. It has a dielectric constant of 2 to around 7. And moist wood has a dielectric of 10 to 30. So anything with a high water content is going to be easy to see with a capacitive sensor. Okay. Again, number of different values here for our dielectric constants, right? Air has a reference dielectric of 1, and then we're referring to that for different products. Okay, so and during the lab, and I'll put the link for the lab video under this guy. During the lab, we're going to look at a number of different components, plastics and metals, and see whether and pieces of wood, and see whether our capacitive sensor actually sees those units. Okay, all different types of applications. Right, this one here is from the Allen Bradley Fundamentals of Sensing. Let me just pause here, and I'll show you that textbook that's available at this link. All right, so this is probably the best textbook that I found out there on sensors. This is Allen Bradley's Fundamentals of Sensings. It is 175 pages, and as you go through, it goes through all your outputs and wiring, 2-wire versus 3-wire, gives you the basics on limit switches, And then it has different chapters on inductive sensors, capacitive sensors, which we're talking about right now, ultrasonics, and then photoelectrics. So again, the Allen Bradley Fundamentals of Sensing is probably the best textbook that I found out there for proximity sensors. So their list of applications is liquid level sensing, looking at product filling lines, plastic part detection, pallet detection, and then they're saying irregularly shaped products. So let's take a look at some of the diagrams you can see on a Google search. Right here you can see this is a capacitive sensor. They're looking for the presence of the pills going by. And so remember that by placing this in close proximity to the pills, by them going by, it'll see a difference between air and the dielectric of each of the pills. And it'll be able to give us not a count on each of them going by, just the fact that this is still running on the line. Now over time there will be a buildup, looks like, of powder on the outer casing of the sensor. So they'd have to come by and wipe that clean, otherwise it would give us a false output. Okay, other ones they give you is carton detections, right? So if you've got cardboard boxes and stuff that are going by, you may use a capacitive sensor. This one they're saying, easy now. This one they're saying that you can see inside the milk carton. Now this looks like this diagram looks like a photoelectric sensor, but you can be able to see inside of a container. Let me see if I've got a better picture to look at that. Again, this one is looking at what's inside of the cardboard box here. So they've got the capacitive sensor here, but we know now, based on what we've looked at already in this slideshow, that the distance here is way too far. And if we go back one, the distance here for a capacitive sensor is way too far. Again, it basically has to be within, half an inch or an inch max of whatever it's sensing. But it can be able to look inside of a box to see if the box is actually full. Okay, with this one, it's looking at plastic parts. You can see the tolerance here is quite close to the tops, and it's just making sure that the bottle caps are on top of here. Is it looking at every one of them? No. So again, this one is probably just making sure that the line is still running through. Okay. If we're using this one for liquid level sensing, or for looking at what's inside of a cardboard box, then you can change the sensitivity of this sensor. On the back end, there is a little potentiometer. And so in this case, you can negate the actual wall of the tank. So you can change the sensitivity so that the wall of the tank is not sensed, and then it can actually see the liquid that's inside of there. So again, the way that you do that is with the potentiometer on the back end. Here's another fill sensor, right? So again, they've placed a plastic screen on the outside of this tank and bolted it in. And then this guy can keep track of, low and high limits here. And by changing the sensitivity of the sensor, it can negate the plastic or the glass barrier here. And it's actually looking at the powder that's inside of the tank to provide that output. Okay, this one again is that different mounting considerations for the side of the tank, again from SiC manufacturers. Here in this textbook, they've shown the cylindrical components. But again, if you're doing liquid level sensing, you're probably going to have something like this. And again, you can change the sensitivity of the sensor. It won't be able to detect the plastic outer casing of the tank, but will be able to detect whatever liquid is inside. So again, you can have a high and low limit just by placing these capacitors in there. And they're not going to fail because there is no contacts. There is nothing that can fail inside of them. It's a transistor that's turning on and turning off. Okay, you have to keep track of your dielectric contents here, because here you can see that this guy is going to work because the glass wall has a dielectric of 3.7. We can drop down the sensitivity so it no longer sees the 3.7, is able to pick up the alcohol that's inside with the dielectric constant of 26. But here, this is never going to work. If we're looking for flour inside of a container, well, once we drop down the capacitance value with the potentiometer so it can't see 3.7, well, there's no way it's going to see something like flour with a dielectric of 1.5. So there is a limitation when you're looking at liquid or powder level sensing, in that if the dielectric of whatever's inside of the container is lower than the actual tank wall, then you won't be able to see that liquid level sensing. The other way you'd have to do that is you'd have to change, put a window here. But again, I don't think that's going to work with something with this low of a value. With this guy, you'd probably put an ultrasonic sensor on the top, have a sound wave bounce down, and then that would give you an analog signal out to tell you the exact level in the tank. Okay, again, this one is for an extruder machine. They have the plastic pieces in there, the plastic pellets. They've got the low and the high limits. Here they've got almost like a manometer, and you can put your capacitive sensor there to look at your level sensing as well. Okay, other applications they've got from different textbooks: level sensing inside the tank, outside the tank, looking at boxes going by. This is most likely going to be a full electric. All of these guys here with the boxes, stacking of different components, looking at breakage and reels and stuff. These are going to be photoelectric sensors. But liquid levels or particulate level inside of a tank, you could easily use a capacitive sensor. Flow control, you could also use a capacitive sensor. For fills, you could use a capacitive sensor as well. And for detecting products, you could use a capacitive prox as well. Excellent. So advantages are that they can detect metallic and non-metallic components. They can see through certain materials. So they can see through tanks, they can see through cardboard boxes to see that the cereal is inside of the cardboard box. They're solid state, so they have a disgustingly long life compared to relay contacts, and there's all kinds of mounting configurations. Disadvantages are that they have a really short sensing distance, so basically 1 inch or less. They say they're sensitive to environmental factors. That's just because if you have something build up on the outer casing of the sensor, it's looking for a change in dielectric. If you have all kinds of crap that's built up on the front face of the sensor, that's going to trip off the sensor without having anything in front of it. What else does it say? Not all selective for its target control of what comes close to the sensor is essential. I don't know what they're talking about there. All right, guys, so hopefully that gives you the basics on capacitors, or specifically capacitive prox sensors. I'll put the link in for the lab that we're going to do with these guys, and you'll see what different types of materials a capacitive prox sensor can actually see. All right, guys, thanks for watching.